Hello, everyone. Welcome to the last lecture for 1610. Um, just a couple announcements before we start. Another reminder that the department symposium is next week on Tuesday, which will be online. Be presentations from undergraduates that have done research over the past semester. There'll be talks from graduate students and from Professor Higgins. So if you're available, I'd encourage you to tune in for some or all of that. The final project is up now. This is will be done entirely in the rstudio.cloud, and it's due a week from today, on Thursday the 7th. If you need more time than that, just let me know. But the goal is to get just about everything done by the end of next week, so we can get everything graded in time for grade submissions. There'll be office hours next week for both myself and the TAs if you need any help with the final project or finishing up any of the other assignments. All right, any other class logistics questions before we start? Okay. So today we're going to be talking about applying some of the things that we've talked about in this class to ongoing debates and attempts at gathering evidence about COVID-19. If you've been trying to follow this as evidence has been coming in, it's been pretty confusing. So, for example, here's like an actual infographic that was being passed around a couple days ago, and people were mocking on Twitter as being almost completely not understandable. And unfortunately, a lot of the way that information has been presented about what we've learned so far has been kind of this type. This is supposed to show something about how like different death rates are changing in different countries, but yeah, I don't think anyone could get anything out of this. That being said, there is a lot of good information out there. This was, I think, just yesterday out in the Atlantic. This sort of big primer by Ed Young that I would highly recommend people read if you're interested. It basically goes through sort of everything that we've learned so far and just basic information about the disease and things like that. And so there is a lot of good information out there. And I'm hoping today to also provide you with some tools for thinking about how to analyze this deluge of information that you may have been seeing. So I should start with a few disclaimers. So one thing we've talked about repeatedly in this class is that statistics isn't just sort of a black box thing that anybody can apply. Ideally, we want to have people that have domain expertise in the thing that we're actually studying. Those are the people that can understand best whether we're making the right assumptions about our data and whether and can understand the conclusions that we actually get out of these statistical tests. And so I do not have that training for this. I'm just mostly relying on other people that do. But again, if anything I say here contradicts something that an expert is saying, you should take their word and not mine. The other disclaimer is that things are changing very quickly. I finalized these slides like 24 hours ago, and even since then, a few things have changed. And so, this is really just a snapshot of what's going on at this moment in time. And within the next couple of weeks, even a lot of this information might be out of date already. And so the goal for today really is talking more about the techniques that are being used to analyze this data and make decisions, right? And this is really a case where we need to use these statistical principles because even though there's a lot of uncertainty, we have to make decisions right now about what to do, both at a personal level and also at like a government policy level, right? And so we can't just say that we don't know. We have to quantify what things we're uncertain about and maybe get ideas about how we could be more certain about them. So the goal here is not really to talk about, to advocate for like particular decisions that either you or the government should be making, but just talking about some of the techniques that we've used in the class to try to understand better this information that's coming in and how can we make decisions with it. So I'm going to talk about three different sort of short case studies. First, we'll do kind of a warm-up about applying some of the Bayesian statistics stuff that we've talked about last week to making a medical diagnosis. Then I'm going to spend a big chunk of the talk talking about how we can get confidence intervals on things like infection rates. And then finally, I'll talk about the debates over what kind of predictive models we should be using to predict infections in the future. Okay, so let's start with thinking about how we can figure out what disease someone has. And so you might have seen infographics like this that were going around. That, of course, the best way to diagnose having COVID-19 is to get a test, but those have been in short supply. Often you need to qualify in certain ways to even take those tests. And so people wanted to know just at home, based on their own symptoms, can they say something about whether they have COVID-19 or a different respiratory illness? And so there were infographics like this, right, trying to show what symptoms are common in COVID-19 versus things like the flu and the cold, which you might confuse for coronavirus. And so the stats question is, how can we go from some kind of graphic like this that basically shows the rate of different symptoms under these three different illnesses? How could we use that to actually make some kind of conclusion about what illness we currently have? Right. So we have some symptoms. And the question is, how do you read this chart, and how would you try to get like at least a rough numerical estimate of probabilities? Right. So example, for the fact these three checks here says that dry cough is a very common symptom with COVID-19, but it's also a common symptom for flu. Right. And so the question is, if we have the symptom, what should we conclude about the disease? And so this fits pretty naturally into this Bayesian framework we've been talking about, right? What we want to do is we've observed some data, which is the symptoms that we have or the symptoms that we don't have. And what we want to do is estimate a probability that we have each of these different possible diseases, right? So here we're just going to restrict ourselves to the only respiratory diseases is some kind of cold or a flu or COVID-19, right? And so if we want to estimate this, remember, we need basically two things to run Bayes' rule. One is that we need prior probabilities, which is how likely just in general in the population we think having these diseases is. And then we need some conditional probabilities, which is for each disease, how likely is it to produce each of these symptoms? Okay, so let's think about the first ingredient here, which is the prior probabilities, right? So this is basically telling us before we even try to figure out what our symptoms are, right? How likely is it that if you have some kind of respiratory illness that it's one of these, which of these three is the most likely? This is a really hard thing to estimate, especially right now. I mean, first of all, it's going to be very different for different people and very different in different places in the world. It's going to be very different in different places within the US. Even within New York State, for example, there's probably like an order of magnitude difference here in COVID-19 infections between downstate and upstate New York. So I'm just going to this is mostly going to be some hand waving here. We don't even have, not only do we not have great numbers for COVID-19, we also don't even have very good numbers for cold and flu. Usually most people don't get some kind of official diagnostic test for these diseases, so we don't really know. And we also don't have a great sense for how the recent lockdowns have had an impact on these other respiratory illnesses. So I'm just going to use some like very rough order of magnitude estimates here. So for reasons that I'll discuss near the end of the lecture today, the number of COVID-19 infections over the past month or so in the US is probably something like 10 million. And colds are definitely way more common than that, at least in a normal winter, spring season. And flu is maybe somewhere in between. So again, these are very rough numbers. The COVID one we have some evidence for. The other ones are basically just rough guesses based on typical rates and assuming some reduction based on the current lockdowns. So the idea here is that the prior probabilities is that that colds are very common, right? At least on a normal year, most adults in the US get 2 or 3 colds, so they're very common. Flu is less common, but also not super uncommon. And coronavirus is still only impacting a relatively small segment of the population. So even before we try to list out our symptoms, right, we could have some but our guess would be that that coronavirus is a less likely option for our respiratory symptoms. Okay. So the other thing that we need here is conditional probabilities, right? Which is for each disease, what's the probability that it's going to produce each of these possible symptoms? And so that's basically what this kind of chart is, right? It's telling us how frequent different symptoms are under each possible disease. Of course, to actually run this, we're going to need numbers and not just checks. So we could just make some sort of rough estimates here. So frequently maybe means something like 0.9. So right, frequently, if we say COVID-19 frequently produces fever, then maybe that's something like 90% of the time. For sometimes, maybe that's like 50%. Little is 10%, and rare is 5%, maybe. Again, these are just my rough guesses. If you actually wanted to do this in a quantitative way, we would need real numbers here and not just these checkmark charts. One last question is what to do about these red boxes that say not. And so assigning a probability of 0 to things is something we almost would never do in statistics. I mean, for example, even if colds cannot produce breathlessness, you still might have breathlessness as a symptom when you have a cold because you might have something else, or you might misdiagnose yourself as having breathlessness when you really don't, right? So we can't put a 0 here, right? And so we don't want to, right? In statistics, we almost never want to have an absolute thing that something can't happen, right? So it almost certainly is possible to at least think you have breathlessness when you have a cold, right? So we'll put in maybe like 1% or something for these nod ones. And so, yeah, so these are our conditional probabilities, right? And the conditional here is what we mean is that this is the probability of the symptom given the diseases, right? And so, right, these things, none of these things like sum up to 1, right? This is saying that if you have COVID-19, then there's a 90% chance you'll have a dry cough and a 10% chance you won't, right? So each of these little boxes is its own little separate probability distribution, which is the probability of having or not having each of these symptoms, given that you have these diseases. Okay, so we have our components that we need now, right? So what we want to compute is the probability that we have each of these diseases given our symptom, right? And so how can we combine the prior and conditional probabilities to get this? So here's a few possible options, right? So which of these is the right form to use here to compute the probability of a disease given symptom? All right, so how can we combine our prior and conditional ingredients here? All right, see an A and a C. Anyone else want to guess? Okay. All right, good. Yeah, I'm seeing. So yeah, I'm seeing a lot of C's, which is the right answer. Right. A is also pretty close, but we do need this normalization factor in the denominator. Right. That yeah. Otherwise, if we forget that normalization factor, we're not going to get a probability distribution here that sums to 1. Right. So yeah. So the Bayes rule here is C, right, which is that we take our prior times our conditional probabilities and then just normalize by this marginal likelihood. Okay, so let's work through like an example of this. So let's imagine the only symptom that we can conclusively say that we have or don't have is a dry cough. And so right, we're going to use Bayes' rule here, right? So the probability that we have COVID-19 given that we have a dry cough, that DC here stands for dry cough, we're plugging into Bayes' rule. And so on the top here, we have our prior probability of COVID, which is 6%. And then we have our conditional probability of dry cough, which I'm getting from our table here. And then we have our marginal likelihood in the bottom, which I'm just leaving there for now. We can do the same thing for the other two possibilities, right? So for flu and colds, we can also multiply these things together. And the way to get this marginal likelihood, again, is we just know that these things have to sum up to 1. So the marginal likelihood here is just the sum of these 3 numerators, right? And so, sorry, yeah, that should be PDC, not ST for general symptom. Yeah, that should be DC here. You're right. And so, yeah, the denominator here is just the probability of anyone in the population having a dry cough from any of these three illnesses. So normalizing these, right, we end up with, right, this has shifted us from our priors, right? We've used to think that a cold was most likely, but if we know someone has a dry cough, now we're shifting to flu as our best guess, right? That dry coughs are pretty unlikely if you have a cold. So it's probably one of these COVID or flu ones, and flu is a lot more common in the population. Okay, so usually we won't just have a single symptom. If we want to get strong evidence for some kind of disease, we're going to need multiple symptoms. And so the question is, how do we incorporate multiple symptoms into this Bayes rule? And so, there's a question too about that. Right, this denominator doesn't matter for relative likelihood, which is right. So that's often why we can kind of ignore it, which is that, right, these numerators here give the relative likelihood of these three, and so we just need to normalize them to sum to 1, right? All that this denominator is doing is just making sure these three numerators still sum up to a correct probability distribution. Okay, so how can we deal with multiple symptoms? So technically we can't with the simple table that we're given. That table really just talks about one symptom at a time. But a frequent kind of assumption that we make is what's called a conditional independence assumption. And so this is this assumption that this is true, which is that the probability of having two symptoms is just the probability of having one symptom with this disease times the probability of having another symptom with this disease. Right. So this is called conditional independence. It's not full independence. So full independence would be if the probability of S1 and S2 was the product of S1 and S2, right? Here, there's this extra conditioning on the back. But this is just saying that if you have some disease, you're sort of like flipping a coin for each symptom separately. And so whether or not you have a dry cough doesn't have any relationship to whether or not you have a fever. And so this is almost certainly not true, right? Many of these symptoms are related to like similar underlying kinds of pathologies in these diseases. So this is a kind of silly assumption, but it might be relatively reasonable for at least a couple symptoms, especially if these symptoms are somewhat uncorrelated with each other, right? Or they're somewhat different measures of the disease. And so, so we can, at least for a couple symptoms, we might be able to make this assumption that these symptoms are conditionally independent given the disease. So if we make that assumption, then we can do things like, let's say we have two symptoms here. So we have our symptoms are breathlessness and we don't have a runny nose, right? So we do have this breathlessness symptom and we don't have the runny nose symptom. We can again use Bayes' rule, and I forgot to copy in the correct denominator here, right? But at least in the numerator, right, what we're doing is we're looking at the probability of COVID given these two symptoms. We have our prior probability of COVID, and now we have this kind of joint conditional probability up on the top. And so what we can do is just break that up into its two separate pieces, right? So our conditional independence assumption is letting us break up the probability of having both of these symptoms is just the product of their individual conditionals. And so we end up with, right, we can plug in our numbers on the top here. We have our prior probability and the probability of not having a runny nose with COVID, which is high, and the probability of breathlessness with COVID, which is also high. And again, the probability down here should be B, no RN, not DC. So we can do this for cold and flu, and again, just normalize these numerators to sum up to 1. And so in this case, we end up with a very high probability of coronavirus, right? Which is that of COVID-19 specifically, right? Which is that for these other two, this pattern of symptoms of breathlessness without a runny nose is very uncommon for either flu or cold. And so even though our prior probability of COVID was low, this posterior probability ends up quite high, right? Because once we know these symptoms, now this changes our evidence. Okay, so this is similar to things that we talked through last week, right? And just one way of summing this up is that these symptom frequency charts that have been passed around are useful, but they're really only one ingredient in actually making an inference about making a diagnosis for yourself. right? And sort of the two other steps we need to do with Bayes' rule is, first of all, we need to know something about the prior probabilities. I mean, we could just assume that they're all the same, but that might not be a good assumption. And then finally, we also need to use Bayes' rule to kind of flip these conditional probabilities around, right? And specifically, part of this kind of flipping that's happening is that we normalize across diseases, right? So for example, right, at least based on this chart here, dry cough, even though it occurs very frequently in COVID, it's not a super diagnostic kind of symptom for COVID because it also occurs a lot in flu, right? So if you want to make a diagnosis, you can't just look at each square of these things independently. What we really need to do is to use Bayes' rule and properly do this normalization across the different diseases. Okay. Any other examples? Any other questions on this first example? Okay, so we mentioned here one of the important factors we need is this prevalence estimates of the diseases. And so a question is, how can we try to actually estimate this? So this is a really critical thing to know, not just for doing this Bayes rule operation, but for doing planning for the future, right? So we really want to know how many people in the US or in any country have built up some immunity to this disease already, right? That might change a lot our estimates of how risky things would be to loosening some of the current lockdowns. And so one way to try to do this is to look for people that have antibodies. And so people that have had confirmed cases of COVID, we know that they have antibodies in their bloodstream. And so this might be a good marker of people that got infected and now have some immunity. And the kind of critical point here is that there might be lots of people that never got a confirmed test, but still have antibodies. And this could be because they were never able to get a test, or maybe they never even had symptoms, right? Or they never had symptoms that were serious enough that made them think that they were infected, right? And so there's been a lot of debate about how common this is not to be asymptomatic, right? But we know that it's definitely possible. So, right, what we'd like to do here is get some kind of measure of how prevalent antibodies are. And again, this is going to vary a lot by region, but at least we can get some estimate in the population for certain areas of the country. So one study that looked at this a couple weeks ago was this study that it was a study done out of Stanford, and so they were measuring things in Santa Clara County, and what they did is tried to randomly sample people in Santa Clara. So they tried to randomly recruit people to have this antibody test to try to estimate how common antibodies are in that population. And so this is this paper I'm referencing. It's a preprint, which means that the authors have written it up and posted it online, but it hasn't been peer reviewed in a journal yet. Part of that is just because this whole process has been moving so quickly. So yes, there's a lot of issues with these studies. The sampling bias issue that was mentioned in chat, we're definitely going to talk about in a minute too, right? Getting a random sample of people is a very hard thing to do. So we're going to talk through both what the study can tell us and maybe what it can't tell us. Okay, so first let's start with just a basic question, which is, right, let's say we have some test, and this is not a perfect test, right? Sometimes it gives false positives, sometimes it gives false negatives. And we use this test, we measure a few thousand people, and we get some rate of positives. So, 1% of the people give a positive result, or 5% or something. And the question is, what should we actually estimate? We want to make some inference about the actual population here, and try to estimate what fraction of the population actually has antibodies. Right, and the challenge here is that these positive test results are coming from two different kinds of sources. So some of these are true positives, which is that the person we're sampling really has antibodies and the test correctly detects that they have antibodies, right? And so the chance that someone really has the disease, we're going to call P. This is the thing that we're trying to estimate. And then the chance that the test gives a positive conditional on the this person having the disease, having the antibodies, I'm going to call true positive rate, right? So one kind of positive test is coming from this, which is that people that actually have the disease actually have the antibodies, and the test correctly detects that. Another kind of positive are false positives, which is that this person we're testing doesn't have antibodies. And so I'm going to call that 1 minus p. That's the chance that a person in the population doesn't have antibodies. And we get a false positive here, right? We get a positive anyway. So there's some false positive rate that even though this person didn't have antibodies, we mistakenly think that they did. And so the final rate of positives that we get, this PR, this is what we're measuring in our study, is going to be a sum of true positives, which is this term here, and false positives, which is this second term, right? And so the idea is that this positive rate is something we're measuring. True positive rate and false positive rate is also something we can try to measure through calibration studies. And so if we know these three things, then we can solve for this P, which is the inference we're going to make about the population, right? So if we just rearrange the terms here, we get this formula, right? Which is that we take the difference of our positive rate minus the false positive rate divided by the difference between the true and false positive rates, right? So again, just sort of working through the math, this is the model that we come up with this relatively simple set of assumptions. We can think about this equation we came up with as basically a little inference model. It's a pretty simple model, right? But it's a model that has two parameters, which is the true positive rate and false positive rate. And so once we set those dials in some way, then we can plug in an observation, which is this PR, an observation in our sample, and it's going to spit out an inference about the population, right? And so, again, as with all models, right, this model may be a good or bad model. It's making certain assumptions about the world. But given these assumptions, we can take something in our sample, which is this positive rate we're measuring, do a little bit of basic algebra to it, and then pop out an inference about the population level of antibodies, right? And this model here should make some intuitive sense. So for example, if the positive rate we observe in the population is the same as the false positive rate, right? If we try plugging in a PR here that's the same as the false positive rate, this is going to pop out a P of 0, which should make sense, which is that if the rate of positives that we see is the same rate that we'd expect even if no one has antibodies, right? That's the false positive rate, then we're going to assume probably no one has antibodies, right? Or at least this test can't distinguish from just a P of 0. The other extreme is that if our positive rate is equal to the true positive rate, then this equation here is going to be true positive minus false positive divided by true positive minus false positive, which will spit out a 1, right? And this should make sense too, that if our positive rate is the true positive rate, that means that this is how things would look if the whole population has antibodies, right? If the whole population has antibodies, the positive rate we observe should be this true positive rate, the chance of correctly detecting that someone has antibodies. So this model here is basically, if you look at this like as a function of PR, this is basically just a kind of simple slope and intercept line, right? So we're just going to scale between these extremes. So if PR is equal to FPR, we spit out 0. If it's TPR, we spit out 1. And if it's something in between, we're just going to linearly scale our guess of P. Note that this model could potentially spit out something that's less than 0 or bigger than 1, right? That can happen if either this model is a bad model, or if just from sampling errors that we have a mistake in what we believe about one of these rates or about the rate in the population, right? But that's okay. If it spits out something less than 0 or bigger than 1, we'll just call that like a 0 or a 1. Okay, so we have this relatively simple model here, right? Again, we have to figure out these two parameters, TPR and FPR. Then we can plug in a positive rate and it'll spit out a population guess. So this is what the study did. I'm skipping over a lot of stuff that the study actually did. So for example, they do this they did all this reweighting stuff and things. So that's outside the scope of stuff we talked about in our class. But right, the basic operation they're doing is they tried to estimate these parameters. So they estimate the true and false positive rates they're partially using data from the manufacturer of the test. They also conduct their own in-house studies a little bit. So the The true positive rate is we take people that had confirmed cases of COVID, so they should all have antibodies, and the test is pretty good, so like 94% of the time it detects it. False positive rate is we take blood samples from people that were the blood samples that were collected before this virus emerged. So we take blood samples from like last year that should might have antibodies to other kinds of coronaviruses, but should not have antibodies specifically for COVID-19. And the false positive rate is also pretty good here. So out of the 401 samples, only 2 times was there a false positive. Okay, so we've estimated these parameters, and then they went out and measured from a little over 3,000 people in Santa Clara County. They went out and measured how many of them had antibodies. And they found that the test produced 50 positives out of those 3,330 people. Right, so this is a sample observation. This PR, this 1.5% is a sample observation. And so we can plug it into our model here. We plug these 3 numbers into our equation and it pops out a 1.1%. Right, so this is saying that our estimate of how many people in Santa Clara County have antibodies is 1.1%. So is this what, so let's try to put this number in context a little bit. So there's a population of about 2 million people in Santa Clara County. So this means that something like 20,000 people in the county have antibodies. And notably, this is a lot higher than the confirmed case count in Santa Clara, which was, so there's only about 10,000 people there that had a confirmed test. And so if this is right, then this means that the number of people that have antibodies is like 20 times larger than the number of people that got a positive test. So this would be good news in a number of ways. So first of all, it means that there's lots of asymptomatic cases, which means that the fatality rate of COVID-19 is actually lower than we thought, right? That a lot of people that are infected are not actually having symptoms, and so they weren't really counted properly, right? But this means that only about 5% of the people that are getting infected are having any symptoms at all. And of those, maybe something like a few percent of them are dying later on, right? And so, so this would mean that the infection fatality rate here is a lot lower than we thought. And it also means that there's more people that have immunity than we thought, right? It's still only 1%, so it's not like a herd immunity thing, but right, this sort of implies that maybe a strategy of trying to just let immunity build up in the population might not be totally unreasonable. So the study has been very controversial. There's some big name statisticians that are on the study, and there's some big name statisticians that are very opposed to this study. And there's the controversy settles on it's around a number of different things. One issue that was already brought up in the chat is this, how good was the sampling that they were doing? Right. So getting independent samples, especially for something like this, especially when people don't want to like leave their house to get blood drawn, is kind of challenging. So what they did for this study is they put up Facebook ads for people to participate. There was also some controversy over the wife of one of the people that was running the study sent out emails to various groups with language that had not been approved by the IRB of recruiting people. And so some of the ways that the study was advertised, people took issue with. So there's a sort of issue about how the study was advertised. There's also potentially a potential issue here, which is that what if you had symptoms and weren't able to get a test through traditional means, through the government or the county or something, and those kinds of people maybe are more likely to volunteer for the study, right? And that was one of the, in like some of these emails, for example, it was saying, maybe you've had symptoms and you want to know if you really have it or not, so you should sign up for this study, right? So that's going to be a biased sample of the population. That's going to be people that that already are more likely to have antibodies. So this is one issue. The second issue, which we're going to talk about a little bit more, is what we'd really like here is not just a point estimate, right? This 1.1%. What we want to know is the confidence interval. And we might be a little worried about this because the number of positive results we're getting in this study, so both in the calibration data we're using and in the study itself, is pretty small, right? So in the false positive rate calibration data, for example, right, they tested 401 people and 2 of them came up positive. And so the false positive rate we calculate would be very different if it was one person or three people, right? That would be a big swing versus two. And so that should make us a little bit worried that if this data set were a little bit different, then maybe these results would be wildly different. Right, so we need to think about what kinds of uncertainty there are in our calculation and how uncertain is this final result, right? So are we really sure it's 20 times, or are these results consistent with a sort of a wide range of possible antibody prevalences? Okay, so we want to answer this question. So there's a number of possible approaches here, right? But what's an approach we've talked about in this class to try to get a confidence interval out of this model? Bootstrapping, permutation tests, a rank sum test, or a power analysis. Okay, so which of these could we apply to our model to try to get a confidence interval? So there's a number of ways to get confidence intervals, and in this study they actually didn't use any of these, right? But there's a method we've talked about in this class. It's a very general purpose method for getting confidence intervals that we could apply to any model, right? Which means we can also apply it easily here. Okay, see a couple answers. So power analysis. Power analysis won't give us a confidence interval, right? Power analysis could help us if we decide ahead of time that we want a certain level of precision, then it could tell us how sensitive our experiment needs to be, right? So power analysis can do sort of the opposite, which is that if we have an idea of how much confidence we want to have in our result, we could design our experiment based on that, right? But yeah, here we're going the opposite direction. And so, so the right answer here is A, bootstrapping, right? So remember, permutation tests are kind of similar, but permutation tests are only good for doing null hypothesis testing, where we're purposefully breaking our data set and seeing what the results look like. So here, right, bootstrapping is a way that we can see how sensitive our result is to the details of our data. Okay, so to do bootstrapping, we're going to do this in R. So I'm going to write a very tiny R program to do this. So I made a little custom function that implements our model. So we haven't really talked about custom functions in the class here, but right, the idea is that I'm making a new function called numinfected. It has 3 arguments: the positive rate you see in the population and these true and false positive parameter rates. And then I'm going to multiply by the population of Santa Clara County. So you plug in a PR, TPR, FPR, and it'll pop out a guess of how many people have antibodies in Santa Clara. There's 3 different data sets here that we're using, right? We're using these 2 calibration data sets. So we have a data set of people that we know are negative, and we can see how often we get positive results there. So 2 out of those 401 were positive. We can have a data set of people we know are positive, and see how often we get positives, and most of them are. And then we have this is that actual Santa Clara data, which is we're measuring people in this population. We don't know what the population rate of positives or negatives is, and we're getting 50 positives there. There's a question in chat too about could we use power analysis here to say something about confidence? People definitely do try to apply power analysis to data. The problem is that it's a little bit tricky, right? So usually we want to do power analysis when we're planning an experiment. The problem is that if you do a power analysis on a significant experiment, it will always tell you that the experiment was properly powered because you're using the effect size that you found in this data, right? And so if you happen to get a large effect size in this data just by chance, right, and then you do a power analysis on that effect size, it'll say that you only needed a small study, right? And so this kind of post hoc power analysis usually doesn't give you valid information about whether the study was a good idea or not. Okay, so we have our function and our data, and so we can run our model here, which is that we're going to look at the mean number of the mean rate of positives in our actual data and the mean rate of positives in these two calibration data sets. We plug into our simple model up here, and this pops out this 20,000 number that I mentioned before, right? And again, the number of confirmed cases here is like 1,000, right? So that's the kind of thing we're comparing to. Okay, so this is if we just put in these point estimates, right? We're getting a single number here for the positive rate that we measured and these two calibration rates. And so, yeah, so the way what we want to do basically is we want to try to figure out whether this study was underpowered or not by using bootstrapping, right? We want to figure out is what if the data had been a little bit different? And so the first version of this we're going to do, we're going to take our model and we're going to put this do 10,000 in front of it, right? And we're going to do 10,000 resamples from our data set. So here what we're doing is we're saying, remember, this is our data set of like 3,000 people in Santa Clara. What if like slightly different people had shown up that day, right? This bootstrapping is that we're resampling from this data set as if it were the population, right? We're sort of pretending we're running more experiments here by resampling. And we want to know how much variability is there in these estimates, right? So we're jiggling around our Santa Clara data set here and looking to see how much that changes our outcome from our model. And so this is what we get. So here I'm showing a density plot of our guesses. So you can see the average guess here hasn't changed, right? Their average guess is still 20,000. In general, bootstrapping is not going to change the middle where our best estimate is, but it does tell us something about the spread here, right? And so based on resampling this data set, this tells us that, right, if this data set were slightly different, we would have estimated maybe somewhere between like 15,000 and 25,000 people. Right. So that's at least some variability here, right? That maybe we can't really say 20 times, maybe it's like somewhere between 15 and 25 times. And so that's definitely some amount of uncertainty, although still we're like way above the confirmed cases, which is this orange line here, right? All the way down at 1,000. So this is basically what the authors did in the paper. Again, they didn't use bootstrapping, but they published a confidence interval that was something like this. So something like 15 to 25,000 people. The problem here is that this, what we're doing here is this, yeah, so this is the 95% confidence interval here, yeah, it's like 13 to 29. The problem is that this bootstrapping that we just did is just resampling the Santa Clara data. It's not taking into account the fact that there's uncertainty about the false positive rates and the true positive rates as well, right? So remember our model here, right? Our model, these true and false positive rates are like parameters in our model, and we're plugging in this PR. So the thing we just did was only bootstrapping the positive rates from the Santa Clara samples, but there's also uncertainty in these true and false positive rates. And the uncertainty in the true positive rate actually is not a huge deal. The false positive rate one, though, is a big problem because if our positive rate is really small, which it is in this sample, right, it was like 1.5%, I think, right? And so if our positive rate is really small, then we're subtracting off the false positive rate here in the numerator. And so if our false positive rate is even off by a little bit, it's going to dramatically change how big this numerator is, right? And right, it could be that this numerator here is supposed to be 0, but our false positive rate is a little bit too low, for example, right? And so, right, so this was one of the main complaints lodged against this paper, was they should have also incorporated the fact that there's uncertainty in these true and false positive rates. So we can do a different version of bootstrapping here. It looks almost the same. But instead, we're going to, instead of just resampling D, we're also going to resample our calibration data sets, right? So we're going to say there's some uncertainty in the true and false positive rates as well that we're also bootstrapping. And so that gives us this distribution here. And this distribution is quite wide. So you can see the model occasionally even produces negative proportions, which obviously doesn't mean anything. That's just saying that it's indistinguishable from 0. Right, and there's really a very large spread here. So the 95% confidence interval is between 2,000 and 35,000 people. Right, so what this tells us is that based on this data, both the calibration data and the actual Santa Clara data here, it's really hard to make any conclusions about antibody prevalence. It could be, so this data is consistent with maybe only about like 2,000 people having antibodies. which is more than the confirmed case count, but not by that much, right? Just saying there's like twice as many people with antibodies as people that got confirmed tests. It could be as high as 35,000. So it could be that there's like massive antibodies there, right? This data is really just, it really is just hard to know, right? And there's a little, basically just too much uncertainty in these that when we do this bootstrapping, we get this enormous confidence interval. And so, right, that means that at least by itself, this study maybe has somewhat limited value for making conclusions. It doesn't mean that the antibody rate is low or high. Specifically, it basically just saying there's a huge range here. So yeah, I'll talk in a few more slides about how we can maybe combine this kind of evidence from this study with other studies or something like that. But at least by itself, it's a little hard to draw conclusions from this. So as I said, there's been like a lot of debate about this paper. So Andrew Gelman, who's in the Columbia Stats Department, wrote a whole blog post about this. His blog is kind of interesting in general if you're curious about things like this. So he came out very strongly against it, saying that he thinks the authors owe us an apology because they basically made a statistical error. Other people had more nuanced opinions about this, but there was also a question in chat maybe last class or the class before about like where to watch these kinds of Twitter fights. And so here's at least some of the people that I think have had good opinions about this, in the sense that they tend to have to be good at explaining the evidence and describing the kinds of controversies that are going on. And so, again, there's other levels of complexity here. People have, this of course also gets tied into like political and economic opinions about what kind of policies we should do. But I think there are a lot of interesting just statistical questions here as well. Okay. So we're going to move on to the last section of the lecture, which is about what kind of models can we use for not just thinking about what the current rate of infections are, but what the future trajectory is going to be. And so this, of course, is really important for making decisions, right? That there's lots of kinds of trade-offs that people are trying to make, again, both in their personal lives and at a policy level. And so we need some kind of model of what is going to happen over the next weeks and months and years. And so we've talked in the class that there's kind of a trade-off in different types of models. So there's on the one end, there's models that are very constrained, where models that are built with lots of assumptions about how the world works, about how they think this process actually occurs and how infections occur. So they also, what that means is that they're kind of inflexible because they make lots of assumptions, but they also have a small number of parameters. Okay. All right. And so on the other end, we have models that make lots of assumptions, make very few assumptions that have a large number of parameters, right? So on the other end here, we can have models that make very few assumptions about how the world works, which means they're very flexible, but it also means that you need lots of data to constrain them, right? Instead of being constrained by assumptions, they're going to try to be constrained by looking at lots of data and figuring things out. And so at least in the epidemiology world, a lot of the traditional models are down at this end. And so we'll briefly talk about these again, these SEIR models that make lots of assumptions about how diseases spread, and they have a relatively small number of parameters in them. There's some things that are sort of in between, where you try to you make a lot of assumptions, but you also do a lot of simulation about how people interact with one another. And then at the other extreme are these models that don't know anything about infections or anything, right? They're just treating this as basically a curve fitting exercise, which is that we have some data, it's moving in a certain way, and we're trying to predict where it's going to move next. So, right, one question is, what kind of model should we select on this spectrum, right? And so the question here is, if we add assumptions to our model, that what will happen, right? Is the answer that A, it's going to always help our predictions, B, it's always going to make our predictions worse, C, it might help if our assumptions are right, and D, it'll hurt if our assumptions are right. Okay, so what would be the impact of moving in this more assumption direction on our models, more assumption heavy direction in our models? Oh, great. Yep, I'm seeing some C's, which is right, which is that adding assumptions is a great thing as long as those assumptions are right. If we add assumptions, what that means is that the model, there's going to be less kind of sampling error in the model, right? The model can depend less on our data and make better inferences because it knows more about the world based on assumptions that we've baked into it. And so this is again the kind of traditional epidemiological approach. So we actually talked about this way back in lecture 2. At the time, I presented this as like a fun aside that would never impact us in real life. But there's a bunch of versions of these models. Maybe the most common one is variants of this SEIR model, which has a lot of assumptions about how infections work, and so it assumes that people start out susceptible to the disease. They're exposed to the disease for some period of time. They're then infectious with the disease, and then finally they're either recovering, right? And there's also some probability of fatalities at each of these stages. And so these models can produce all kinds of curves like this, right, where you assume that people are starting out susceptible here, right, and then over time we're seeing lots of infections until finally people are recovering. And there's very few parameters in this model. There's basically for every arrow here is a number in this model, which is how quickly do people move between these boxes, right? If you're susceptible, how likely is it that you're going to be exposed? How likely, what's the fatality rates here? If we're running this over a long period of time, we also have to account for the fact that the population size might be changing from either births or maybe immigration into a region. And so the nice thing about these models is that they only require a very small amount of data, right? So we only have to estimate, like 6 to 10 numbers or something. And so what that means is that even with a small amount of data, we could maybe figure these out, right? We need somewhat sensitive experiments to figure out these numbers, but we might not need a big quantity of data. The other nice thing about these models is they are kind of extensible. So here's the link to the one version we looked back in lecture 2. There's like a bunch of different other versions of this. They can make other kinds of assumptions about how this works. You could assume that maybe even some of the people that recovered, maybe they lose their antibodies over time and become susceptible, right? So you can add extra arrows here, right? But the idea is that, these are models that are based on how we think this data actually is being generated, right? This is sort of a model of like the data generating process, and it should be relatively easy to fit with a small amount of data. On the other end of this are these assumption light models, and the primary model being used at the federal level in the United States is one of these kinds of models. It's from this Institute for Health Metrics and Evaluation, so I'll call it the IHME model. And this kind of model is directly using the death rate curve, so it's looking at the number of deaths per day, and it's directly fitting a function to this. So it doesn't use any information about susceptibility or exposure or anything like that, right? It's just looking at deaths per day and trying to project this forward. So internally, it actually uses a Bayesian ensemble prediction approach, which we mentioned a little bit last week. So what it does is it takes data from all of the countries that we have data from. So the data set they're using here is quite large. It's basically like death rates for every region of every country that we have data from. It pools them together, which in statistics terms, pooling basically means that it assumes that the disease is similar but not identical across different regions. So some regions may have worse outbreaks than others. Some regions may have worse fatality rates than others or something. But in general, there's going to be something shared across them. And then it does this Bayesian ensemble prediction where it has multiple, it sort of has like different kinds of assumptions about what the impact of social distancing is, but instead of choosing any of them, it just makes lots of different predictions and then averages the results based on how well they fit the evidence, right? So ensemble predictions is another sort of version of not committing to assumptions, right? Which is that instead of picking a model, we're going to just put in all the models and let the data try to sort out which one is right. So these models look something like this, right? So there's observed deaths so far, and then it's going to make predictions about what's happening in the future. So you can go on if you just search for IHME, if you go on their website, you can see the updated versions of these predictions. So this kind of direct data fitting, right, assumption light kind of approach has a lot of advantages. One advantage is that you only need data about daily deaths in each region. And this is, for the most part, information that we have. I mean, of course, these numbers are also subject to lots of caveats. There's reason to think that these are certainly undercounted in most regions, especially, well, it might vary a lot by region as well. And so, yeah, so there's almost any of the data that we're looking at here, there's issues about whether it's trustworthy and whether it's sensitive enough. But the hope is that this death rate data is relatively good compared to things like case counts, right? So these other models ideally would use information about like how many confirmed cases there are, right? How many people are infected in a region. And that is something we really don't have a good estimate of. It's very dependent on testing. In the United States, as we've seen like surges of more testing in regions, you see massive increases in confirmed cases, which is almost certainly coming from the testing changes and not from some underlying process, right? So all of these data points are have their caveats, but that the hope is that the death rate data is at least a little bit closer. A lot of people, often, even if people aren't tested when they're in the hospital, you can also test post-mortem, right? So you have some more time and things. So that's one advantage, is it just uses the kind of data that we think is maybe the best, even if it's not perfect. It doesn't require us to build in lots of assumptions. And so it doesn't require us to like know exactly how effective the different social distancing measures are, right? It just puts in lots of possibilities and then tries to use the data to figure out how things are changing over time. The fact that it's so flexible means that it can use lots of data. So as more and more data comes in, its predictions can get better and better, right? That's not really true for the SEIR models. They were, once you have a small amount of data, then we'll know the parameters of those models, and they can't really make use of more data beyond that. The other advantage is that using this pooling approach, they can use data from everywhere in the world. And the especially useful thing is that there's regions that are farther ahead than the US is in terms of these death curves. And so that also helps a lot with the predictions. There's also a lot of disadvantages to this kind of a super flexible model. So one problem is that because it's so flexible, it means that when you only have a small amount of data in some region, the fits are going to be really unstable. And so that means that, for example, you're going to have really wide confidence intervals, right? That it's really going to be very unsure. We're trying to predict with this whole ensemble, but if you just have a small amount of data, you don't know which model is the best. And it's just sort of pushing all of them together into a mush, right? So when we have a small amount of data, this kind of model is probably not very good. Also, the question of whether pooling data across countries makes sense is a little maybe questionable. Different countries have reacted very differently to this. And so it gets a little bit tricky about whether it makes sense to try to average across countries in this way. Another issue is that this is basically just predicting what's currently happening or what has happened in other countries, which is all the first wave of this. This kind of model can't really tell you anything about like what might happen in the fall, for example, right? It can't predict a resurgence of the virus because we haven't seen that anywhere yet. And so that the model doesn't even know that that's an option. Another disadvantage of these kinds of models that don't have a small number of interpretable parameters is that we can't think about kind of counterfactual simulations, right? We can't think about, well, what if we did this? What if we changed the course of disease in this way? How would that change the things in the future, right? These predictions are, they're predictions about the future, which means that things that we do now can change what happens in the future, right? And these models, these curve fitting models don't know anything about that, right? They're just modeling these deaths. They don't understand where they're coming from. They can't tell you whether implementing some policy is going to change this in the future. So here's an example of this link here. This is an example. This is using one of these SEIR models. And so I'm not going to get into all the details of this, but right, this you can basically see here. Here's like the different kinds of compartments in the model. You can like turn things on and off here. Here are all the parameters of this model. So this model has these are the sort of traditional SEIR parameters, which is how does the disease get transmitted? How long are people infectious? Things like that. Here are some parameters about how how likely we think people are to need to be hospitalized, how long do they spend in the hospital, things like that. So if you want to make predictions about hospital usage and how many beds we need, you need to estimate these parameters too. Right, but the nice thing with this kind of model is that you can try to fit these to your data so far, and then you can say, okay, what if in the future, right? What if we are able to get our R value down to 0.2, something like that, right? And this R parameter here is a measure of infectiousness, which is how many people on average does each person infect. So if you're infected, how many other people do we infect? And so if this value is above 1, then then we see these enormous outbreaks. They really only stop coming down once we start getting immunity in the population. If R is less than 1, then we see these decreasing outbreaks, right? And so for example, the estimate that in like New York State right now is that the R is maybe around 0.8 or something, at least in New York City, right? And so what this is saying is that if we just kept on our current trajectory, right, we'd expect to see things keep coming down. If we reopen some things and we get maybe R comes back up to 0.97 or something, right, this is going to tell us how many extra infections and deaths we would expect. Right, so this is a nice thing about these kinds of assumption-heavy models with these interpretable parameters is they let us run these simulations forward. So after saying all that about the advantages and disadvantages of this IHME model, how well has it actually been working? And again, this model has been very influential for setting policy in lots of parts of the U.S. So here in gray, I'm plotting the gray line in the background is the prediction that this model made on March 25th, which seems like a lifetime ago now. It was a month ago. And in blue are the actual daily fatality rates in the U.S. And so I'd say this seems like a reasonably good prediction. It's certainly underestimated, at least a bit, right? The actual things here are pretty much within the confidence intervals. That's the light gray here is the confidence intervals from the model, right? And so the model did a decent job of capturing right where this sort of peak was going to be and at least approximately where it was going to be inside these intervals. Although, right, we do have to note here that the confidence intervals here are quite big, right? So part of the reason that the data matches our predictions here is because the prediction is quite, the range of predictions here was quite large on March 25th. So for example, just in terms of like projected total deaths, on March 25th, the model predicted somewhere between like 38,000 and 162,000, which is quite a large range. Now that there's more data in this model and we're farther along in this wave, the confidence intervals are smaller, right? So it's predicting now that like an upper limit of more like 123,000. Right, and just for context, like the actual number of deaths so far is around 56. So I'm actually not sure what's going on with their lower bound here. It's a little lower than the actual number of cases. I think this model I think is operating a little on like a 1 week lag or something like that. That they wait for partially this is to account for the fact that deaths aren't reported on exactly the day that they occur. So yeah, and again, there's been a lot of controversy in the statistics community about whether this IHME model is good or bad. There was a paper that there's at least some statisticians that came out saying that we really should be using like SEIR models, right? We should be using models that use basic parameters about the disease, and that'll allow us to have a model that doesn't have these huge confidence intervals, that doesn't fluctuate so much over time, right? Because it builds in all these assumptions about things that we know about how diseases spread. A maybe slightly more compromised kind of position would be saying that really we don't have to 100% choose, right? What we could do is try to use all these models. If there's cases where the models make very different predictions, then that's where we need to actually look and see, right, why is this model with lots of assumptions making such a different prediction? Is this because it's making a wrong assumption? Maybe the assumption heavy model is bad, or is it because our curve fitting thing is missing something about how diseases really work, right? And so again, there's a lot of opinions about this. I'm maybe mostly in this camp of all of these models have their uses. They might also be useful in different contexts. So there might be times or reasons or regions or certain kinds of decisions where some models are better than others. Okay. Any questions on this part? Okay, so I wanted to sum up today, just trying to talk a little bit about like where things stand right now. So so just recently, in the past few days, someone did a meta-analysis of these studies of infection fatality rates, and so we didn't talk about this in the class, right? But a meta-analysis is essentially taking multiple studies and trying to combine the evidence from each of them, right? We can think about this like in a Bayesian sense, where right, every new experiment that we do adds some extra evidence and increases our confidence about the what's going on in the population. So this is at least what the current version of this looks like. They're actually updating this as new information comes in. But so the current version looks like this. Every line, every row here is a different study that's been done of trying to estimate how deadly this disease is. So you can see, for example, this first study has a confidence interval between here and here, which is, right, the confidence interval is somewhere between like a 0.18% fatality rate up to a 1.2% fatality rate. And so what you can see is there's a decent amount of variability among these studies. The Stanford Santa Clara one we talked about earlier in this lecture is this one here. And this one is on the lowest end, right, of estimating a relatively low fatality rate, because they're claiming that there's many more asymptomatic cases than we originally thought. So if we combine across all of these, we end up with this final confidence interval down here at the bottom, which is that the infection fatality rate is maybe something like 0.75%. Right, we still don't know exactly. It could be, there's still a kind of big range here between like 0.5 and 1, but right, this is the value that we get from accumulating all of this evidence. Right, so at least just taking like the middle of this confidence interval as our current best guess, right, we can just do some basic math to say, right, there's been about 56,000 deaths in the US, and so that means there's something like approaching like 10 million people that have been infected in the US. This infection fatality rate also tells us how bad things would be if we decide to just relax all of the lockdowns, right? So one thing we don't know here is how much of the country would get infected eventually if we don't have any kinds of distancing policies. But if we even if we conservatively say maybe it's like 60%, like maybe above 60%, herd immunity is enough to keep this down. But if 60% of the country is infected at this fatality rate, then we'd end up with 1.5 million deaths, right? And again, there's some uncertainty about this still, but the answer would basically be between somewhere like between 1 and 2 million. Right, so this infection fatality rate, it's like maybe a little bit lower than we initially thought, but still high enough that we probably would not want to. And again, there's lots of different kinds of factors that go into making decisions here, right? But I think most people would consider this an unreasonable number of deaths to allow in the country. So if we can't just relax everything, right, what's going to happen next? And I don't really have any more knowledge about this than any of you do. I think almost certainly it's going to look something like this. So there's an interesting post. This post was actually put up like about a month ago, but it has still has been one of the few things that has been relatively right since that time. And so the author here of this post described sort of two phases to this epidemic. The first one is the hammer, which is meaning these sort of very restrictive kinds of lockdowns that we've been having in the US, meaning that we just try to contain what's been happening so far. We try to buy ourselves a little bit of time to figure out what's going on. And then at that point, we can enter the second phase, which he's calling the dance, which is that we want to basically keep this R value below 1, right? Meaning that we want, on average, when someone's infected, we want them to infect one person or less. That'll mean that we're not going to have out of control infection. And so what that basically means is that we're going to have to slowly relax things. And every time we relax something, we're going to have to try to do something to decrease R, right? Which could mean doing things, right? Maybe there's like drugs that we can use. Maybe we can get the fatality rates down in different ways. But it's basically going to be this kind of adaptive thing that if we see R start going back up, then we need to undo whatever the last thing is that we did. And this is basically, at least in New York State, the approach that they're taking. So here's a slide from one of Governor Cuomo's presentations earlier this week. If you're interested in more information and following information, Governor Cuomo's presentations have been pretty good. They're usually relatively, of course, there's always political spin to any of these things, but they're usually relatively fact-based. And so, right, the policy going forward in New York State is going to be that we try to slowly relax things. So, for example, the first thing that's being relaxed this week and next week is starting to allow manufacturing back into most parts of the state. But if we hit any of these warning signs, which is that hospitals are down to 30% capacity or the rate of transmission is noticeably above 1, then we need to undo whatever we just did last time, right? And so the hope is that we can sort of achieve this balance of slowly opening things up, with the end goal being that over time there's going to be greater immunity in the population, which will help, and eventually hoping for a vaccine that at least for some of the people in the population can also give them immunity. And so, right, with this, the kind of unfortunate answer here is that there's not just going to be a distinct point when things open back up. It's really going to be this kind of protracted process of testing out what kinds of things we can open without allowing outbreaks. Which means that it's really hard to really predict more than a few weeks into the future, because we really don't know exactly what the impact of different interventions is going to be. Right, but as we're going forward, again, there's still going to be a large role for statistics and gathering evidence and understanding our uncertainty about lots of things, like in these bullet points of what things are the most effective to do, right? What things are going to cause the least kind of economic harm or other kinds of harm to people. And so, right, there's still a lot of questions about how we're going to do this. But there has been I think one conclusion from following the stuff is that there really is a big community of scientists and researchers that have been pouring hours and hours into this. There's been lots of, again, this is really rapidly changing, but really just over the last couple of weeks, there's been tons of studies on this. In this chart, for example, you can see, like if you look at the dates here, like a lot of the data they're using here it says April, but that's kind of an understatement. It's really like within the past 10 days or so that a lot of these have come in. And so we are learning a lot, and that does give me hope that our inferences about what's going on are going to get better and better. Okay, so I just wanted to, we're about out of time here, so I just wanted to just finish up with some final thoughts for the class. First of all, I wanted to say thank you to the TAs that really did a great job being flexible and helping me figure out how to transition this class sort of mid-flight from one format to another. And I know they've also helped a lot of you in office hours to keep up with all the material. And I also wanted to say thank you to the students in the class. I know for many of you, this has been a really hard time for all kinds of different reasons. And honestly, I've been just incredibly impressed that people have still been watching the lectures and listening to the recordings and keeping up with the material despite all the kinds of pressures that everyone's been under. And so thanks for helping us get to the end here. We still have the final project, but it's been really impressive how well everyone has really gone along with all of these changes. And so thank you for that. All right. Any last questions before I sign off? All right, thanks everyone. So yeah, just a reminder, the final project is up now. I'd encourage you to take a look at it soon. Just make sure that you don't have any technical issues with RStudio, anything like that. The TAs and I will be here, online here over the next week to help you out. Thanks so much, everyone.